Here we have one moving object stacked on top of another with the possibility for friction in between the two. Let's call this surface of contact between crates A and B surface 1, and this surface between crate B and the ground surface 2. And suppose B is being pulled to the right by this rope, then the two crates could be moving, possibly accelerating, to the right. And there's a lot we could learn from this scenario. Let's start by breaking down the free body diagrams, focusing on the contact forces between the two crates. So in this simplified picture over here, we might first think of the force of the bottom crate pushing upwards, holding up the top one, the force on A due to B. But even if you know Newton's third law, it can be easy to overlook the fact that as the bottom crate pushes up on the top one, the top crate is also at the same time pressing downwards on the bottom one, the force on B due to A. So here's a tip to help remember that this force exists. Imagine holding up something heavy, balancing it on top of your head. Of course, your head is pressing upwards on it to hold it up, but you could feel it pressing downwards on you. And note that this is not a force of gravity right here. This is the contact force from the bottom of the crate pressing down on the top of your head. So that's a Newton's third law force pair right there, which is like this pair right here. So that's what's going on at surface 1. At surface 2, there's the usual normal force from the ground pressing upwards on crate B. Note here, the ground is only touching the bottom crate. The ground is not touching the top crate, so there's no interaction between the top crate and the ground. Okay, so those are the vertical contact forces. But if the gator is pulling hard enough that the crates are accelerating to the right, then there could also be horizontal contact forces between them, friction at this surface, and that's what we're most interested in right here. Now, if that's happening and B is accelerating to the right, we know that it would be the rope pulling on B to the right, but what would be carrying A along with it? The rope is not attached directly to A, so it's not the rope pulling on A. If B is moving to the right and A is moving with it, then the only thing that could be accomplishing that would be friction at this surface, dragging A along with B. Here, like if I have this mass on the piece of paper here, my fingers are not touching the mass, but I can accelerate the mass to the right because friction between the mass and the paper, that's pulling the mass to the right. And it's just that sort of friction that would be dragging the top crate along with the bottom crate. So here, again, is that simplified picture looking just at a few of the horizontal contact forces. That right there, the force of friction at surface 1 to the right, this would be the force that makes the top crate move along with the bottom crate. That's the top crate being dragged along with the bottom crate right there. But here again, even when you know Newton's third law, it's easy to overlook that if friction is dragging the top crate to the right, then there must be an equal and opposite force of friction pushing against the bottom crate to the left. Now, this force here can be hard to sort of intuitively understand, so I recommend visualizing a slightly different scenario. Suppose that we have a much more massive crate stacked on top of a smaller one, and you're trying to pull the smaller one out from underneath the top one. So if you're pulling it out, it might be hard to pull it out because the weight of this one pressing down causes there to be friction here. You have to fight against that force of friction right there that you're fighting against. That is what the top crate here is exerting on the bottom crate right there. So this Newton's third law pair is like this pair right here. And now if there's friction between the bottom crate and the ground, then here's that force of friction right there. Let's call it FF2 for the force of friction at surface 2 to distinguish it from FF1 here, this force of friction pair at surface 1. Okay, so these are just portions of the free body diagrams. Now let's put them all together. Here's the full FBD for the top crate. Gravity pulling down on it, that's an external force, since here's our system. This internal force pair right here is this force and that force, and this internal force pair here is this force and that force. So if we focus just on crate A here, we see that its FBD is pretty simple, just balancing vertical forces and friction pushing crate A possibly to the right. Nothing else is going on here. Crate B's FBD looks much more complex. We've got that tension here, its own force of gravity pulling down on it, and that contact force from the top crate pushing down on it. So there are two downward forces on crate B. The force of gravity due to the interaction with the Earth, and this through the interaction with the top crate. Also, two leftward forces of friction on crate B. There's the friction from surface 2, and this friction here from surface 1. So if you can construct this full set of diagrams here, you've done a pretty good job on understanding what's going on here. We'll consider multiple scenarios that could result. And before we get into those scenarios, let's consider the vertical portions of these two FBDs. Let's look at the vertical sums of forces. So with crate A, we see that FAB minus this force of gravity must equal 0. Those are balanced. So we know that this contact force here is equal to the weight of the crate. Nothing unusual there. Summing forces on B. So here's this normal force from the ground balancing out the force of gravity on B and that downward pressing contact force from the top crate, FBA. So that sum is 0, which means that this normal force is the sum of these two. And if the force on A due to B is equal and opposite to the force on B due to A, if these have the same magnitude, then this is just equal to the weight of the top crate. So the total normal force exerted by the ground on the bottom crate is the sum of the two weights. We factor out a G there. And in this sense, we see how the ground is holding up both of the crates. Now, it's not the weight of the top crate acting directly on the bottom crate. The force of gravity on the top crate is balanced by this contact force, and that contact force is acting downwards on the bottom crate. So it happens to have the same size as the weight of the top crate, but it is a contact force, not a force of gravity. This contact force happens to have the same size as the weight of the top crate, but it is not a force of gravity. Okay, with that distinction made, I think we're set up here to now consider a number of scenarios that will depend on how hard the gator pulls.